the Higgs Center summer school in theoretical physics. I'll be giving 5 lectures over 5 days on introduction to gravity, and there's somebody coming from Durham who's also speaking on anomalies. Yes.
Yeah, I saw the.
You saw the announcement.
But when are you coming exactly?
It'll be the last week in May.
Okay.
Yes.
And maybe hopefully we can meet. I will contact you by email. So.
Okay, I'll be there, but I'm also staying on in Edinburgh the 2nd week.
Okay.
It will be the 1st week in June.
Okay.
So I'll be in the United Kingdom from the last week in May and the 1st week in June.
Okay.
So I'll arrive there, whatever is the date of the school, I arrive the day before.
Okay.
Yeah.
Are you just gonna be in Edinburgh, or if you have plans to travel close to London or somewhere?
No, I'm only going to be in Scotland because I'm going to be visiting Edinburgh. I'm also visiting St Andrews.
Okay.
Yes, and so it'll be about a 2-week trip. But anyway, if you have students who want to come to the school, I think that would be fine.
Yeah, sure. I will advertise that.
Yeah, but tell them to apply. They have to apply quickly because they're going to give some money for accommodation, but only until it runs out.
Okay. Yeah.
So tell them to move.
I think probably it is circulated in Portsmouth. I will check it. So, yeah.
Okay. Anyway, yes. But I won't be coming to anywhere near the London area, unfortunately.
Okay.
But I mean, most times I go to England, I have done that. But after my parents died, they lived in Liverpool. I've stopped visiting England, and that I haven't been to England since before COVID. Actually.
Okay. Shall we wait a little bit more, or we can start? The people are still coming.
Maybe a couple of minutes. Yeah.
Let's wait a couple of minutes.
Yeah.
Sure, no problem. I think in Copernicus we usually wait for 5 minutes at least.
Yes.
But then you see it has like a negative, so to say, feedback in the sense that people know that we wait for 5 minutes and then they come 5 minutes later.
Yes.
It's like saying the speed limit is 10 miles an hour over whatever is posted.
Yeah. Oops. Turns out that I can even
This
press.
page is still, Alex, in fact, your next page, the text is too small. Maybe you can increase a little bit.
Yeah, but after that it will be all large. So I
Yes.
did not need
Okay.
to.
Okay, very
It will
good.
be just a picture. So it's okay. Don't worry.
Okay. We are stable now in number of participants. Hello, everybody. Let's start our seminar. Today we have a pleasure to listen to the talk by Alexander Vikman, and he will tell us more on stable ghosts. Please, 1 hour.
Okay, so thanks a lot for inviting me. It's my pleasure to participate in the seminar, to give a talk, and to listen in other seminars. So feel free to interrupt me. Let's have some discussions. That's always very nice. It would be even nice in person, but okay, online works too. So I will update you on the stable ghost. I think I have said part of this material I presented in this conference like a bit less than a year ago, and now we have some update on that. But I will probably also repeat things which some of you have heard during this conference 1 year ago. Okay, so this talk is based actually on these two papers. One is this PRL, which was with Cédric Defayette and Shinji Mukayama, and it was called Ghosts Without Runaway Instabilities. And another one is in JCAP, and there to Cédric and Shinji also around health jointed. And so we had like a larger paper with much more discussions. So, and many more systems. Actually, this one is more interesting, and this one is more recent, slightly less than a year ago. Okay. So you see, we don't need to read all these details, so therefore the text is small. Good. So now you see part of my motivation is evolving, that there is this old known problem of gravity, and as Hawking and Hertog was pointing out in the paper, which I like the title, Living with Ghosts, they were saying that perturbation theory for gravity in dimensions greater than 2 requires high derivatives in the free action. High derivatives seem to lead to ghosts, and then you see they say states with negative norm. So this is what I don't like. So I don't want to have states with negative norms. I want to have normal systems in a sense of normal quantum mechanics in normal Hilbert space with usual scalar product and usual probabilistic interpretation and Born rule. So therefore, if you want, that's not that kind of living with ghosts, what I'm going to describe you. And instead, I use definition that ghosts are actually dynamical degrees of freedom with negative mass. Or if you want, kinetic energy unbounded from below.
Excuse me, it is not a definition of tachyon?
Not really, because tachyon has imaginary mass or negative mass squared. That's the difference.
Negative mass, not mass square. Okay.
Exactly. This is very good point, because people colloquially use both kind of words, but in reality, it's like to say negative sound speed. But in reality, when they say negative sound speed, they mean negative sound speed squared. Very good point. Yes. So we want to talk about real negative masses, and you will see why just in a second. So if you say that something has negative mass, you could also say, why should we care? Following this, very, very pessimistic views. But Hawking and Hertog kind of said part of motivation. Let me tell you more why could be we interested in ghosts. First of all, you see, there is interesting cosmology, which one could have. There is this phantom dark energy, super accelerated universe with growing Hubble parameter. Then it's interesting for early universe because you could have bouncing universes, you could have oscillatory universes, you could also have inflation with blue spectrum of gravity waves. So this is interesting for our misunderstanding of what dark energy is. In particular, why? Because, for example, it's still not forbidden to have growing Hubble by current data, okay? So therefore, it's interesting to understand whether it's necessary implies some pathology or some strange coupling or something else. Or maybe one could just have ghosts as they are. Then another thing is more like, if you want, ideological. You see, one could ask, why all normal laws of nature, or usual simple laws at least of nature, are second order? So they correspond to second order equations of motion. Why would not we use higher derivative systems or higher order equations of motion? And you see there, we know that there is this Ostrogradski theorem, which is embarrassingly from mid 19th century. And the point is that high derivative systems have actually ghosts. And that's usually considered to be a big problem for such systems. And I'm going to mention how to see it in simplest cases. And then you see a related issue is, it's kind of interesting that, yes, indeed, usually we don't use high derivative systems exactly because of this Ostrogradski problem. On the other hand, cubic equations of motion, so containing the third derivatives, are actually the simplest models for chaotic behavior. Because as it's well known, we need at least three-dimensional phase space in order to find chaos. And in reality, really, even some electric circuits, like Chua circuit, they have this third order equations of motion. So actually, one could even use such things in technology. The question is, okay, third derivative is probably hard to get from an action, but maybe you could have for fourth derivatives and so on. So it would be interesting to understand that. Then coming back to what Hawking and Hertog were saying, it's actually very well known from the times before I actually was born, as a result by Kellogg-Stelle, that if you write a gravitational action in the form of normal Einstein-Hilbert term plus curvature squared term, so namely Ricci scalar squared, probably one should call it now Starobinsky term, and then Weyl term, in that case, gravity becomes renormalizable. Okay, this is very interesting. Would be very nice to understand, especially in view of the following points, that this R squared term still perfectly well fits all data for inflation. Okay, so Starobinsky inflation survived, and it's the oldest model of inflation which is still there. Okay, for all data. And the question is, why can we see this alpha, which is pretty large, it's like 10 power 11 as far as I remember, and there is no beta, okay? Even though both of these parameters are dimensionless, and theoretically they should have just logarithmic running and that's it, okay? So this is an interesting equation on itself because it's known that such systems, they have ghosts. But I'm not going to deal with that because, you know, I will start from zero order approximation. I will do some mechanics. So then there are more ideological questions also related to entropy and thermodynamics, because if you allow for energies to be negative, it becomes very interesting because clearly entropy, by its statistical definition, should be always positive. That it implies that the temperature should be negative. And indeed, for some systems, it's known that negative temperatures can occur. Nevertheless, it's not a usual thermodynamics. In particular, systems with negative temperatures are, in a sense, hotter. They're more excited than those with positive temperatures. Okay, then another thing is kind of related to what's written by above, is that you see all our technology is based actually on electrodynamics. And in reality, there is one fact about electrodynamics which is extremely useful for us, namely screening. So we have positive and negative charges, and therefore we can screen gravity. We can screen electromagnetic forces. With gravity, we are handicapped. We cannot do that. There is usually in all our models, and it seems in all normal theories, there is always only positive masses, only positive energies, at least energies in some sense, and therefore it's impossible to screen gravity. Of course, screening gravity would allow you enormous advantages in technologies, and therefore it's very interesting. Then more related question to that is, you see, if you can screen gravity, you can also probably screen cosmological constant and explain its value, because we have no idea neither how to calculate it nor how to get any number which would be approximately right. And if you want to screen it, most probably it requires some negative energy there. And of course, dealing with negative energies, dealing with negative masses, allow to have you interesting exotic complex objects like wormholes and so on. This is per se very interesting, also whether such things can exist. And more theoretical question is whether gravitons can be massive. Okay, usually attempts to give a mass to gravitons result, let's say, either in Boulevard desert ghost, in nonlinear theories, when we start expanding around Minkowski further than in quadratic order, or if you want, the construction of DRGT, which is perfectly well, operational around Minkowski, still around cosmology, you have modes which are ghosty. Okay, would be very interesting to understand whether it's possible to have massive gravitons without, so to say, punishment. So of course you can add there whatever motivation. I'm more than happy to add it into this list. Okay, So now what I'm going to do is related heavily, it's actually very simple, it's zero order approach to this problem, and it's heavily related to actually this gentleman, and who is actually called Giuseppe Ludovico della Grande Tournier, which we know as Lagrange, and he introduced the notion of Lagrange stability, okay? And in fact, he would not call it Lagrange stability, but you know, as it is like accustomed by mathematicians, they would call later things attributed to other people. So it's a very simple notion that actually the motion is finite. So basically, a system is called Lagrange stable if the motion is finite. It always evolves, it always happens in a bounded region in phase space. That's what you can also call global stability, okay? In reality, it's not what we would intuitively call stability, because intuitive notion of stability is more related to this gentleman, who is Alexander Mikhailovich Lyapunov. And Lyapunov introduced the notion of stability, which is actually super easy, super simple. It means that if you have two solutions, or whatever, other solutions, right, starting close enough, and they have distance delta from each other, okay, then they remain close enough forever. There's a distance epsilons from each other, okay? So basically that implies that if I want to find solutions which are close at infinity of time, closer with epsilon, I can always find such delta for the initial data, okay? In particular, by the way, that forbids all singularities and so on, okay? But it's much more natural notion of stability if you want its stability by initial data, very intuitive. Close by trajectories remain close forever. And actually in this talk, I will tell you that presence of ghosts can really fulfill both these notions, Lagrange stability and Lyapunov stability. Okay, now let me remind you another 19th century stuff. So namely Ostrogradsky theorem. So for us, for poor people, this could be thought as like, let's say we write a propagator, which is for high derivatives. It has momentum power 4. We can just rewrite it as two propagators, and one of them has now a negative sign, okay? Which is usually considered to be the sign of the trouble, and either you need to violate unitarity and introduce their negative norms, or you say, okay, that was negative energy and you need to live with this negative energy. So of course, Mikhail Vasilyevich Ostrogradsky would be rather surprised to see such a demonstration of his statement. His statement was presented in this paper, and as a good Russian, he was writing everything in French. And actually what is interesting, he was writing everything in French, reading in French, but he didn't know English, so therefore he was not aware of works of Hamilton. And therefore, in this paper, he was actually re-deriving whole Hamiltonian analysis, whole Hamiltonian formalism from scratch, just from high derivative systems for everything, basically for generality. He was a true mathematician. So one could basically illustrate it very easily. What is the problem of this Ostrogradsky approach? So let's take a Lagrangian which depends on coordinate, first derivative, and second derivative. So basically, it does depend on acceleration, which is not a usual thing. And then what Ostrogradsky suggests us to do? He says that, however, the coordinate which should be conjugated to this Q is this P1. And P1, as you see, is just the first bit, which is standard one, right? Minus second bit, which actually has third derivative inside. So now what is super unusual is that he would say that the second coordinate you need to consider is actually the velocity of the first, okay? And then basically the momentum which you should look at it would be in that case a derivative over acceleration, okay? And now what happens if we use standard definition, how Hamiltonian and Lagrangian in that case are related, using standard formula, what we would obtain is that the Hamiltonian is actually this first long, so to say, momentum, which was depending on third derivative, multiplied with second coordinate, because q1 dot is actually q2, plus second momentum multiplied with this acceleration. And what is the key point? This acceleration we obtain from equation for P2, and therefore it is P1 independent, because P1 contains third derivative, which was not present in the Lagrangian originally. And then the Lagrangian itself, again, can only depend on P2. It cannot depend on P1, because P1 depends on third derivative. Okay? So what do we see? That actually the Hamiltonian is always linear in P1. So therefore, it's unbounded from above and from below. Okay? And this is, of course, an interesting statement, that you start from generic system, and suddenly you see that the energy is necessarily unbounded from above and below. Okay, let's illustrate it with a super simple example. Sometimes it's called Phys.Rev.Lett oscillator. So basically, we take a normal oscillator with frequency 1, mass 1, and we add second derivative term. And then it's very easy to apply this, what is Q1 P1, then what is Q2 P2, and that gives us this Hamiltonian. Okay. This is, of course, super simple system. It's quadratic, so it's it should decouple, right? And what we see is that you can also do canonical transformation, time independent one, so very standard, just to see the structure, how is it related to negative masses. Because if you apply this canonical transformation after Ostrogradski procedure, then you see that there is kinetic term p squared, however, with minus sign. Okay, and this minus sign, of course, if you recall that the mass should divide this p squared, that implies that the mass of this y degree of freedom is actually negative. Okay, so now we can apply this mechanical analogy for field theory. So this is normal oscillator. This is action for, let's say, cosmological perturbations. And z and cs are two functions depending on time. If we go to Fourier space, we see that Hamiltonian for each mode looks exactly like this oscillator above. And we need to associate this z with the mass. Okay? And omega is then sound speed multiplied with the wave vector. So basically, if we say that the whole sign in front of this action is negative, so z is negative, it implies that the mass is negative. And so it is for normal oscillator. Okay, very briefly, then I will recall you this action, that there are two types of instabilities you can get there. So gradient instability is when the sound speed squared is negative, and that implies just that the oscillator is inverted, okay? And this instability you will see on linear analysis directly, just apply linear perturbation theory, and this would correspond to solutions which are growing with time. And what is very bad about such solutions is that the shorter is the scale, the shorter is the scale at which you look at these perturbations, the faster the growth. And I used to always think that it's a deadly, basically, situation. However, now I am aware that there are some models where the sound speed is very small, and then there is this UV completion which happens, and you can kind of stabilize it by introducing k to the 4 terms in dispersion relation. So basically, omega squared would be in that case minus c squared, k squared, plus k to the 4 with some term, and it still can be in terms of a normal effective field theory. These terms can stabilize you. Okay, and second thing is this ghost instability when z is negative, and that actually you would only see by interactions, because per se linear analysis would not reveal any troubles. This is this negative mass, and simple thing to see what would go wrong there. You could just into this field theory, you can produce two perturbations of this R, and then let's say two photons. They will be connected through some graviton, and then naively this diagram, this production out of vacuum, it's clear that in each vertex you would write 1 over m Planck. So it's 1 over m Planck squared, then this is for amplitude. Then for the rate, it's 1 over m Planck to the 4. So therefore, if you want to look at this production rate per unit time, per unit volume, you would need to multiply it with some dimensional parameter lambda 8. lambda power 8, okay? So of course, the problem is, it's only true in the sense this lambda has this the meaning of the external cutoff. So basically you need to introduce cutoff for momentum for these flying out particles, which is not how we usually deal with such things, right? And it's only possible, of course, if your system breaks Lorentz symmetry. Because if you need to integrate over Lorentz group, this rate of production, perturbative one, would give you infinity, which is, of course, nonsense. And either you need to abandon such systems in general, saying that it's wrong, or you would need to say that, okay, at least this perturbative formalism is not applicable, okay? Very good. So now, so this instability works in the following way. So you have kind of normal matter, it's like scissors, right? Then Gaussian matter, total energy is conserved, time passes, the scissors opening up because Gaussian matter can decrease the energy, normal matter can increase the energy, total energy remains constant. And basically, if you think about ideal scissors, they can open up infinitely, right? So that would be the real problem because nothing can stop them. Nothing, but actually is, as you understand, the whole thing is in the nail there, which is the interaction, okay? And this interaction controls whether this instability is really present there or not. So how unstable can it be? So let's take normal oscillator, Gaussian oscillator. Let's introduce the interaction, quartic interaction. And let's put initial conditions similar to vacuum. But of course, I'm doing classical calculations. So I'm going to plot here the energy of a normal oscillator. By the way, guys, can you hear me still? Because I'm not sure.
We can hear you.
Yes.
Okay,
Nice,
perfect.
everything is okay.
Perfect. No, don't worry. So then I basically plot the logarithm of the energy of the first guy without interaction, right? And as you see, it has a structure similar to parametric resonance, and it increases quite quickly up to enormous values that the log is basically 10, right? After that, basically, the code crashes. What is more interesting is that you see you can change the coupling constant, keep the same frequency, and the change in coupling constant is kind of okay. It's order 1, but you would not expect that this should depend on that. In reality, it reveals very strong dependence on the value of coupling constant. And in reality, you could wait for 600 periods of oscillations till you see the instability. But then the instability will kick in, and it will be very strong instability, as you see. After that, whatever, my code crashed, but of course, one could make it more precise. So the interesting thing is about that is the following, that actually such systems are extremely dependent on coupling constants, and the real instability can appear very, very late, okay? So one could say that maybe this is not a problem because, okay, if this very late means longer than the age of the universe, who cares? On the other hand, it's very hard to say when exactly will it happen. And that also implies that there were a lot of works studying stability of such problems numerically. And that implies that numerically, if you, for example, wait in this picture for 500 periods of oscillations, you will infer that everything is stable, and you will miss the point that just a bit later, the whole thing will go astray. Okay. So let me remind you, so what was our first example of a stable model? So at least first that I'm aware of, we took normal oscillator, coupled it to a Gaussian oscillator, and this interaction potential was actually of this form. Not a piece of cake, not most elegant one.
Oh, we don't hear you.
Yeah. Alex?
Alex, are you here? Please try to say something.
But as this, what was this potential?
Oh, Alex, you got frozen for, I think, 30 seconds.
Oh, really? Okay.
Yeah.
Strange. Okay, so this I have told, right, or not?
Yeah, you were starting talking about the potential.
Yeah. So this potential, you see, it's a normal kind of nice function, but it's not the most pleasant one, and it's not polynomial. What is important, also another interesting thing is that these interactions, they are dying with respect to their normal harmonic parts or non-interacting parts, x squared and y squared, if you go far away in this phase space. So this was the model, and basically how to see it. So let's say this is whole potential, and for lambda less than 1/2 by absolute value, and this is for lambda larger than 1/2 by absolute value. And you would have basically, naively, you can just expand it around 0, and you would immediately see the two frequencies which are there. And of course, they get corrections by interactions. And then you could naively say, okay, by linear analysis, I would infer that if lambda is less than 1/2 by absolute value, then the saddle point is actually linearly stable. However, we need to recall that this is linear analysis, and what actually we need to show in this case is that interactions do not spoil the picture. So linear analysis here is not enough. That's the point. However, it turns out that linear analysis tells you the right thing in reality. So what is lambda larger than 1/2? That's very interesting because you have two such equilibrium points. And actually, one can show that they are Lyapunov stable, even though for potential, they're saddle points. Okay, so which is very funny because usually it's the minimum of the potential. So I will tell you about the left case more because right case is just a bit longer, but in reality, most of things are applicable to two of them. Okay, numerical solutions, this is a bit boring. You see just oscillations, it's all kind of stable. What is interesting in projection of phase space into YPY surface, you see kind of donut shape, okay? So there is time going from red to blue, and you see that the solutions are kind of oscillating between kind of two limit curves, if you want, two envelopes. Okay, you can also do some analog of Lissajous figure, and this looks like some pillow, okay? And if you wait longer, this trajectory will cover everything in this XY space. But everything inside of these boundaries, which are already there. You could guess it's stable, right? So then one could ask, okay, why is it stable? Because as I told you, linear analysis is not applicable. And here for these pictures, I did not start around 0. I put just some random number as initial data. So you can ask, what is the black magic, okay, behind it? This is actually a picture I have taken in the castle of Albrecht von Wallenstein, this notorious military commander in 30 Years' War. As now we live in kind of that time, seems to be, it's probably interesting. I would not be, by the way, surprised if this picture was some weird horoscope provided to Albrecht von Wallenstein by Kepler. So, but basically it's definitely some black magic involved. So what is this black magic, right? Why is it stable? Why can I claim that it's stable? So basically, if you want, we used power of imagination. And in reality, on top of energy, on top of Hamiltonian, there is another first integral. Namely, it's this expression, which I kind of called E. So it has generator for hyperbolic rotations, this Pyx plus Pxy, plus what you would think two energies of a free oscillators, now with both with positive sign, plus this additional piecewise interaction. So one can check that for this system, this expression is conserved. Okay, so this is additional first integral. How we get it? Actually, we looked at systems with normal positive mass, and we thought that this was done by Darboux, but in reality, it was done before, actually long before, you see, 50 years before, by Liouville, okay? And we see, so therefore, when they figure out that for 50 years they were repeating these calculations, you know, I'm not ashamed too much to repeat it again 100 years later, 120. So basically the point is, we have done complex canonical transformation using imaginary unit I, and of course, this transformation preserves commutators, and therefore it preserves the conservation. And therefore, we know that this quantity is conserved. However, now it used to be for normal masses, now it's for the ghost. Okay, so to say what is the global symmetry behind it is kind of not easy, because local symmetry I can also integrate it. I mean, write some infinitesimal generator, but it's not very elucidating, I would say. Okay, so this another first integral can be used to prove stability. How? So you write it in this form, where the sigma, as you see, is just 1/2 of radius squared in phase space plus this hyperbolic rotation generator squared, okay? So now how we use this quantity in order, this E, in order to show that the motion is Lagrange stable, so globally stable. So the point is interaction here was bounded, okay? So therefore, in this E, there was a sigma plus something bounded, okay? Now that implies that E would always be inside these two limits. So it's sigma minus modulus lambda and sigma plus modulus lambda for all times, always. Okay, this is just per construction. So now let's apply these bounds for one trajectory for two different moments of time. Let's say TA, we get this, and TB, we get the same thing. Now the key point is that this E is the same. Okay, and because E is the same, we could immediately claim that sigma A minus modulus lambda is smaller than sigma B plus modulus lambda. And vice versa, that sigma B minus modulus lambda is less than sigma A plus modulus lambda. So that immediately implies that sigma B is less than sigma A plus 2 lambda by absolute value and sigma A minus 2 lambda by absolute value. And this is the origin of this, if you want, donut shape. Okay, so that implies that for lambda less or larger than 1/2 doesn't matter. We always stay in finite region of phase space, doesn't matter with which initial data we would start. This is the key point. So this is what is called Lagrange stability. So we have proven that, and that's the origin of this donut. And you see the sigma is really your just a bit larger than your radius, right? Radius squared. So system always evolves in finite region of phase space. What is also important, you see that if lambda is larger than 1/2, you would say that the sigma B is just larger than 0, which is triviality, and it's just less than sigma A plus 2 lambda. So basically, the shape would not be donut, it would be kind of a sphere, if you want. Okay, so now we can go to Lyapunov stability, and actually in Lyapunov stability, what is very interesting, in his doctoral dissertation in Kharkov in 1892, Lyapunov said the following, that there are such things as Lyapunov functions, okay? So basically, he wanted to consider, instead of energy, some other functions, namely, this function should be at the origin, we should try to test on stability. Let's say this is your equilibrium point. It's 0. Outside, it should be actually positive. And as you see for us, in the origin, E is 0. And outside, for this value is y squared minus x squared, is positive. And actually, if you change it to negative values, it is positive, but only if you have lambda less than 1/2. Okay? So basically, Lyapunov statement is 0 in the origin, positive everywhere else, and not growing. And that it's a trap. If you want, we should introduce on initial data. And that's a statement that if you can find such a function, that implies that such solution is stable in this neighborhood, in which this function is defined around your origin. So basically, we know this function, this is this function E, and we show that for lambda less than 1/2 by absolute value, the origin is stable, Lyapunov stable, okay? So by that, we showed that in this system, the equilibrium points, the only equilibrium point actually, is Lyapunov stable, and the system evolves in globally stable trajectories, which are always bounded in phase space. So basically, these are two quite strong statements which we have done analytically. So Now, the point is very, very quickly, you can write it also as high derivative system. It's a bit maybe aesthetically not pleasant, but it's possible. And you see, I remember last time when I was giving previous part of the talk in this conference, people were telling me that, oh, okay, you use just canonical transformation. It's still secretly that there are no ghosts, and probably it doesn't matter at all. But okay, let's see, especially for global stability. So for Lagrange stability, let's see whether it matters or not, how we do this canonical transformation with imaginary unit. So let's take normal system. So p squared by half 1/4 cosine hyperbolicus. So on the right, you see the phase space with all the trajectories, right? And it's of course clear that the motion is bounded always, and that the origin is stable. It's triviality, right? Now let's do this imaginary transformation. It's canonical, obviously. And now the system is ghosty. However, the potential is not cosine hyperbolicus. It's just normal cosine. And now you see, that's a tricky part, which is usually not very much elucidated. Had we started to use this h bar Hamiltonian, however, with only imaginary values of p bar and x bar, of course, dynamics would be the same. But what we want to do, we want to consider now this x bar and p bar to be real. And therefore, of course, if we treat now this new system just for real variables, the phase space will look like this, because it's a cosine. And as we know, of course, this cosine is a periodic barrier. So if we take, if you want the value of momentum larger than the height of this barrier, then we fly away and the trajectories are not globally stable, right? So, and that's exactly what happens. As you see, these red lines here on this picture, these are the heights of the barrier, and blue trajectories are those which are already unstable. They're infinite. They're of infinite extent. And therefore, they're not Lagrange stable because they don't evolve in a finite region of phase space. Okay, very good. So now, in this new paper, what we have done is we found a much larger class of such stable systems, which are both Lagrange stable, Lyapunov stable, whatever you want. So namely, we took this Liouville example and studied it more carefully. So we have done this imaginary transformation, and therefore the sign is not as by Liouville. And the potential looks like this, where Liouville uses u and v, and this u and v are kind of what is very often called hyperbolic coordinates. And they are given by these two formulas, which are not very nice, where c is a constant, and r in our case is x squared minus y squared. In Liouville case, of course, r is x squared plus y squared. And then you see, what we have proven in this new paper from JCAP is the following, that actually conditions for global stability for such systems are super easy. First of all, this constant, which if you see, it's needed even for dimensional reasons, this constant c should be positive. Then both these functions, f of u and g of v, should be bounded from below. Okay? This is also not that hard requirement. And then last thing, what we want is that if you look at infinity, then this f of u and g of v should both grow faster than u in v power 2 by absolute value. They should be positive and grow faster than the squares, okay? And that would immediately guarantee you Lagrange stability for the story. And of course, you can ask, how is it possible? Again, let me remind you, there is this Dirichlet-Lagrange theorem, and this is super easy statement that if you have conserved energy, then the minimum of your potential energy is actually stable, right? On the other hand, you know that if you have energy which is less than the barrier, right, then the motion is finite and you evolve just in this potential well. Okay, so now the black magic again, this first integral, right? has now the form which corresponds to positive kinetic energy if C is positive, and it has a potential piece which is U. And now if you analyze how this U looks like, you will see that it's needed that that basically these functions G and F, they grow faster than U squared and V squared. Okay, so you see, it's like a direct analog. So you use for this second integral of motion, you think that it's energy, then this is your kinetic energy, which is for C positive, it's positive. Then there is potential energy, and for potential energy, you just require that it builds a potential well. And after that, you're done. Basically, you would know that it's a Lagrange stable. Moreover, what we have found, it's another interesting, very interesting subclass of such systems. Namely, you can take a very general polynomial potential with this same constant Cn for both these functions, f and g. And in that case, you see they are the same constants. In that case, you could immediately see that you can fulfill this requirement of boundness, of providing, if you want, for u a potential well, when n is at least 4. Okay? So if n is less than 4, you cannot do it. So you need, like, you see, you need some interesting interaction to have it. And then, interestingly enough, look at this potential. It's not really complicated. It's just two harmonic pieces, right? X squared, y squared. Wrong sign is just because y is a ghost. Then there is a quartic interaction. This quartic interaction is somehow adjusted by these frequencies. You could maybe say that it's kind of fine-tuning, even though the C is arbitrary here. And then the story continues with this quartic and cubic terms. Okay? So what is, how does it work? If you take this potential and calculate the U potential for the second integral of motion, the one which we use to see whether the system is stable or not, you would see immediately that the first part becomes positive definite harmonic part. Quartic interactions have different signs, so they're not sign definite. But six-stick guys are positive definite. And therefore, this U is a potential well in which the system should stay, and it cannot escape. Because the kinetic energy is positive, and U is bounded from below, and it's unbounded from above if you go to basically infinity in this phase space, in the way, if you want here in configuration space. Okay, so basically the only thing what you need to require that this coefficient as C4 is positive. Okay, so now you can look at this potential energy. Note that this is potential energy for the integral of motion. So it's not your original potential energy. And you can plot it. How does it look like in configuration space as a function of these two variables x and y? And you immediately see, so think about this as if this were your normal potential energy. And you see that there, in some cases, there are 5 minima. In some other cases, there are 3, and in some other cases, there are 1. So the two pictures on the right is the same case. Is just, you see, because whereas the minimum is 1, I thought that it's a bit boring. So the interesting point is just the picture in the middle is a bit zoomed in what is happening on the most right picture. So now you can immediately see a very interesting situation. So the origin is minimum of this potential energy, but it's not absolute minimum. And the red points are new equilibrium points. So these are the minimum of this potential energy, which are novel, which are purely due to interactions. And they are deeper than the minimum in the origin. So now the point is you could see in which cases, by the way, by which ratio of the parameters, which of the cases is realized. So basically you can introduce these omegas divided by C4, C squared. C4 we consider to be positive. And therefore, immediately what you see that there are three possible cases. So case number one is exactly depicted on the left, and that's when you have 5 minima. Then you have case number 2 when you have 3 minima, and case number 3 when you have only 1 minimum. Okay, so the interesting thing is that minima of u, that's what we show in appendix of this paper, that minima of u are actually saddle points of V. So what is very important, that minima of u are of course solutions, they're equilibrium points of your dynamics, or fixed points of your dynamics. And then you see what happens, that actually interactions with ghosts not only have not destroyed stability, right? It actually created new Lyapunov stable vacuum. Okay, so imagine, so you took two systems, you think that you brought them into equilibrium and that they should go astray and everything should get destabilized. In reality, you created new, more stable configurations, so new vacuum if you want. So now I can illustrate how it looks like basically for different parameters, how the systems evolves. You see, it's very similar. It's again some pillows or some basically bounded regions in phase space. Unfortunately, I cannot draw 4-dimensional phase spaces, only like 2, maximum maybe 3. And you see, what is also interesting, you can destabilize if you want the origin. And in that case, it would be an example of a system which is around the origin, it's unstable. But globally, it is stable because this potential u from the first integral gives you a normal potential well. So you cannot escape from there. So there is a region when the instability happens, but then the motion is still always in a finite region of phase space. And it can give you very, very peculiar pictures of how the evolution happens. Okay, so now you could say, okay, so this polynomial potential is better than what we had with this 1 over square root. In particular, we see what is very interesting is that this polynomial potential, it allows for interactions to grow at infinity. So in reality, if before one could say that at infinity our system becomes super weakly coupled and maybe whole stability happens because they are not talking to each other in a sense. Here, this ghost and non-ghost, they are coupled for sure, even at infinities. And what is interesting that it's a huge class of systems which are now absolutely stable in all possible means. And then by Kolmogorov, Arnold, Moser, we could say that small structural changes which we would introduce there. Let's say we would couple this to another system which used to be stable in itself, and the coupling is small. In that case, we could say that the stability would not be jeopardized, so it will be still okay. At least on solutions of very large measures. On some measure 0 solutions, like something strange could happen, but why should we care about measure 0? Okay, so this is very important for us. However, one should keep in mind that maybe with making number of degrees of freedom larger, Kolmogorov-Arnold model theorem works worse and worse, and there will be more and more, so to say, kind of singular but nevertheless unstable solutions if we couple this stuff to something else. Okay. So I'm basically close to finish, and then the question is, which one could pose after seeing all that, is why have not we seen such systems in nature yet? So I don't know, maybe it's gravity which plays the role there, because of course gravity should not like negative masses. On the other hand, you see, gravity is the weakest force, and naively it should not really jeopardize anything there. On the other hand, maybe we just never try to model anything with these negative masses, and therefore even, let's say, in condensed matter. And therefore we just don't see them because we try always to match our observations to something else, all our experiments to some other systems. Okay, so basically what I see, it's a kind of interesting, hidden, secluded and very interesting path. Maybe full of life or maybe not, I don't know, but it can be very interesting path to investigate and to understand. So thanks a lot for your attention.
Okay, thank you very much for your very interesting talk. I see several questions. First, this is from Chinchan. Masood, please ask your question.
Yes, your consideration are for two spaces different. It means X and Y. So one of these oscillators in the X space and the ghost one is in the Y space.
Well, it's just they have it's normal 2 degrees of freedom. I mean, you can still embed them into one normal Euclidean space, right? It's just the equation of the energies, right?
Are you happy with this answer? Masood, is okay for you? Or do you want to ask more?
Yeah. Can you hear me now?
Yes.
Yes, please.
Okay, so sorry. You have taken is the two spaces, one X, one oscillator is in X, and the ghost oscillator, let's call it ghost oscillator in Y. They are in two different spaces. So, but in field theory, it is not like this. They are in the same space. Now, what would happen if you would take them at the same space? It means because your X and Y are two-dimensional, but one oscillator is in the X space and the ghost operator is Y space, and they are separate. You agree?
No. You see, so Masood, sorry for the interruption. You see, if we go to field theory, then we would need to write two fields. Instead of X and Y, we would have psi of X and let's say phi of X, right? So instead of X and Y, we would have psi and phi, let's say, and then we will bring them into interaction. Actually, we are doing numerical simulations, of course, classical, and so far we don't see any real instabilities there for classical solutions. Of course, like I don't know how to do any quantum modeling, but I would suspect that if you do if there any instability in this bosonic system, it should cause you a lot of particles after that. And then it should kind of be semi-classical in some sense at the end. But it's not what we see on computer. On computer, we don't see any instability at all, to be honest. But we don't have any proof, you see. We don't know for how long we need to wait till maybe the instability will happen. Will it happen at all? We cannot say that.
But for
field theory, you see,
classical consideration.
Yeah, it's classical,
Field
of course,
theory, because the field, they are not separate. The ghost part is not separate. If the kinetic term is with the negative sign, it has in both. But in your case, it was that in two separate spaces, the oscillators are only through the interaction. So the main thing is the negative sign in front of the kinetic energy. You see, this is what I want to say. In field theory, it will make a big mixture. So it's a little bit difficult to say that this simple model would have said that in field theory if you have
no. Look,
negative.
Field theory generalization goes in the very same way. You use X and Y as phi and psi, and then you see the thing is in field theory, X is just a dumb variable in the sense that it's just you integrate over it or sum over it. It never appears anywhere. So instead of X and Y, you would have phi and let's say psi. And after that, you write how they interact, and that's it. So that's exactly what we are doing. Of course, the key point that in field theory, the instability is usually caused by the continuum of these degrees of freedom.
Yes.
But you see, classically, at least, so far, we don't see any instability. What is interesting. And one could see there is another very important comment, I think, here, that if you do classical dynamics for these two fields, one ghost and one non-ghost, then if the interaction happens through fields, but not field derivatives, in that case, it's easy to see that the system of two equations of motion, interacting equations of motion, is still hyperbolic. And I think it's even strongly hyperbolic. And because it's strongly hyperbolic, you would know that the maximum rate of instability there, it's fixed by some exponent with some number. So basically, it cannot, the growth cannot be exponential with some, let's say, k dependence, where k is a scale, right? Is a wave vector. So it should be really that the growth is bounded for all modes. And this is very interesting because we know that from mathematics. Of course, it's not quantum mechanical statement. It's just normal classical statement. But okay, we do what we can. But thanks for the question.
Thank you.
Okay, let's go to the next question from Richard Woodard. Richard, please ask your question.
Hey, Alex, nice talk. We've
Thank
spoken about this before,
Yeah.
and you addressed the issue that I would ask you about, I think, a little bit with the last questioner, but let me be sure about this. You are claiming that you can extend this to a continuum field theory?
Look, we cannot extend our analytic part so far, but we can just put it on lattice and see how such things interact, such two fields, without seeing any classical troubles. But you see, the point is...
Really, because it's, as your last questioner mentioned, it should be that the instability is driven by the vast entropy of phase space.
Exactly.
So what I would predict is that, so it doesn't surprise me at all that you could find a cleverly constructed point particle model, quantum mechanical model with finite degrees of freedom that avoided the instability. What would surprise me a great deal is if you could find one that had a continuum degree of freedom that had the instability. And so what, in your lattice issue, what I would predict is that as you increased the number of points in the lattice, you should get more and more. It should be harder and harder to have the system be stable.
You see, unfortunately, that's not what we see. So basically, we were, of course, changing the lattice space, and so far, it's okay. The problem is, for us, it doesn't prove anything, because, of course, we suspect the same thing as you. I mean, that there should be some instability. But it's
one
not...
other thing you might try is to couple the system, to keep it being a finite number of point particles, but couple it to a continuum field theory like electromagnetism. For example, make your particle charged. And in that case, I can't see any reason why you wouldn't produce, you know, infinite numbers of photons paying for it by exciting positive and negative energy degrees of freedom in the point particle system. What cuts that off? What prevents that from happening?
Yeah, that's a good point. However, I think even if you couple it to field theory, that's an interesting exercise. Even if you couple it to field theory, but the coupling is in some sense small, I need to think in which sense it can be small. Then I don't think we would really jeopardize the stability of this.
But see, I don't see any way to keep it small, because there's always higher momentum modes. There's no matter what you make the coupling constant, as the number of I suppose in E&M case, it would be the number of spatial three momenta that are available gets to be larger and larger and larger. You know, you're always going to lose that.
Look, sure, of course. But you see, the interesting thing is, if you put it on computer, let's say, of course, there is always finite. In reality, we just couple it to a lot of discrete degrees of freedom. It's never continuing. So maybe that's also another problem. But the question is whether we really would see this instability. But unfortunately, physically, of course, you see, I'm completely on your side in the sense that there are very good physical reasons why such systems should be unstable. And actually, there would be already good reasons why mechanical systems should be unstable. But for field theory, what can I say? I mean, numerically, that's not what we see. Basically, we were doing even like scattering of wave packages, you know, and the interaction. and nothing happens there. Which is a bit surprising, but maybe it is again related to the point that, and of course we were changing lattice spaces, but you know, it would not increase, and basically would not change anything what we see.
Okay, well, those are my questions. Thank you again for your talk and for answering my questions.
Well, thanks, Richard. Great to hear you. Not to see, unfortunately, but to hear.
Okay.
Thanks.
Let's go to the next question. The next question is from Fawad Hassan. Please ask your question.
Hi, Alex.
Oh, hi, Fawad.
So I think I did not understand one point correctly. So when you talked about the stability in terms of the boundedness of the motion in phase space.
Yeah.
So if you just look at a free particle not interacting with anything, that motion is not bounded in phase space.
Absolutely, absolutely.
So what is wrong with that? What is wrong with excluding those kind of motions?
You see, the interesting thing is because there are a lot of different actually notions of stability. Indeed, just normal free particle, or let's say particle in this periodic potential, but with energies above the barrier height, is not Lagrange stable, just by definition. And of course, it's not really anything wrong. It's just not what is called Lagrange stable. So now I can also explain why do we want to have Lagrange stability, because you know, we want to kind of consider more complicated systems, and we want, of course, to quantize them. And then for quantization, you see all these free particles, so there it's much harder to, basically there is no discrete Hilbert space there, and it's harder to construct. But if you really have a finite motion, let's say in a potential barrier, in potential well, better to say, right? In that case, there is discrete spectrum. And there we would know that the Hilbert space is well defined. Otherwise, of course, you're absolutely right. A free particle, I mean, it's free particles, there's no problem. It's just, it's not by notion of Lagrange stability is stable in this sense. You see, it's very interesting because, let's say in our examples, there are systems which are Lyapunov unstable, so they just would have exponential growth and would strongly depend on initial data around, let's say, 0. However, they will be globally stable in the sense that the global dynamics will be finite. So these two notions are not identical, because also there could be systems with stable Lyapunov solutions, whereas in reality, the global stability you cannot guarantee because you just change. So basically, there's a small island from where you start and you stay there. But if you change this initial data, go from epsilon away, suddenly you fly infinitely far away. So basically, both these notions of stability, Lyapunov and Lagrange, they don't imply each other.
Yeah, so this is good. This I agree with you from the point of view of usefulness, but from the point of view of just classical motions. So you use that argument, you use that statement essentially to rule out the suggestion that your system is well behaved simply because it is some kind of canonical transform of a ghost-free system. And then this was ruled out because in this model, the canonical transform give you a motion which was unbounded in the sense of going the particle going to infinity.
Right, right.
But if that is an acceptable system classically, then doesn't the kind of criticism come back, because now you actually are dealing with a system where both the original system without a ghost and its canonical transform with this complex variable which exhibit a ghost, both of them are now physically valid systems.
You see, that's a good point. In reality, you know, for some of these systems, before you do the transformation, the motion would not be bounded. That's another interesting point. So you see, the model I showed was very easy. I mean, like that was super simple.
Okay, I agree.
potential
I agree. Okay.
can be unbounded from below, because in some cases you will switch the sign.
Good, good, good. I understand. So you're saying that this model is too simple. You can have, in general, you have other cases where this is what I'm saying is not valid. Good. I agree.
Yeah.
Thank you.
Thanks.
Thank you.
Okay. More questions, please?
I see something in the chat. Even
Yes,
though I cannot.
my computer is too small. I don't see any questions in the chat. Yes. I see.
Maybe it's
I don't see any question in chat.
let's say maybe I can see it. Maybe it's for me.
Maybe this is personally for you.
Yeah. Sorry, it's personally for me. Yes. Okay.
Can I ask a question?
Sure.
Hi, Alex. I'm just wondering if you have any, if you thought about any observational test of this
Oh,
kind.
no. Look, this is
Any,
observational test. You see, we are doing mechanical systems of without saying what we are modeling, like it's just a question of if you want mathematical physics, so far. Observational tests would be actually, see what is interesting. Now, for example, Jim Klein is manifestly doing ghosts, okay, without even bothering about all these stability problems. And basically what Jim would do, Jim would tell you that I am an effective field series. He would tell you that this cross section, like we live in the universe, I will have just low UV cutoff. I break Lorentz because, let's say, I don't know, I don't care. It's some frame given to you by CMB. It's odd to me, but you could claim that. And after that, this cross-section can be done very small. So yes, you would produce particles of both type. It will be actually saturated by high momenta, not saturated, but basically dominant by high momenta, right? But after that, phenomenologically, you would say that it's small. Because basically it's a question, how much of these gammas do you see there? Do you see now this Feynman diagram or not?
Yeah, I can see.
Yes, it's okay.
And actually, Jim was doing now even models of dark matter for that. I think he has 2 papers now with manifestly ghosty dark matter. He even wants to boost, basically to give to dark matter a bit more velocity from basically doing such a process. I think it's very brave, to be honest. It's much more brave than what we are doing.
No, I'm wondering, like, if the physical systems with ghosts are stable, I mean, we should find it in any energies, even maybe perhaps in condensed matter systems.
Look, that would be fantastic if we could find such systems in condensed matter. Actually, that's maybe where it's more promising to look at them.
Yeah.
To make
But
some
because
they're
experiments,
stable,
yes.
nature prefers stability, so it should exist somewhere in some particular.
yeah, but you see, maybe there are some other reasons why such things are not allowed. Even though I'm not entirely sure. Definitely some islands of stability that should be definitely possible to have. Why don't we see it? I don't know.
Okay.
You see, like in some, I don't know, some electron traps or God knows where, somewhere, maybe we could see such things.
Yeah.
Okay. More I see one more question from Jeff Kuntz.
Maybe, maybe not immediate to have any physical example, of course. I think there is another question.
Yes, Jeff, please ask your question.
Thanks, Alex. It was a very nice talk. You guys can hear me, yeah?
Yeah, I do.
Okay, great. I was just wondering if you had any comment on how this stability issue relates to PT symmetric quantum mechanics. I know that some of these Lagrangians you show, or the Hamiltonian you show, remind me a lot of this Pie-Uhlenbeck oscillator. I know Professor Mannheim's in the chat. I was wondering if you could comment on, I don't know, I mean, if you just have PT symmetry, or maybe it's not so surprising that it's stable.
You see, that's okay. That's another interesting thing. So, to be honest, we have not checked whether one could look at this from PT symmetric point of view. So what we are trying to do now with normal quantum mechanics, we use standard scalar product and not PT scalar product. As far as I always understood PT symmetric quantum mechanics, I think Philip can correct me if I'm wrong. As far as I always understood, so you have a theory of normal Hilbert spaces, and then all Hilbert spaces of the same dimensionality is isomorphic. So therefore, if you found some system with some Hilbert space in PT, I think you can always map it into standard scalar product and then see how because the operator is Hermitian, you would map it into another Hermitian operator with respect to standard scalar product. So I would say that, yeah, that's interesting, but I'm not sure it is really related because, for example, for us, you see this Lagrange stability, for example, was more about asymptotics of this potential. And I'm not sure this would play any role for PT symmetric quantum mechanics.
Okay,
So
yeah, thanks.
it's interesting to check. I don't know.
Okay, I guess I can comment.
Sure, you should.
Jeff, the issue that Carl Bender and I addressed was how do you handle the negative norm problem? The issue that Alex has been addressing is how you handle the negative energy problem. And
Right.
they're in principle different problems, and they correspond in the quantum theory to different Hilbert spaces. And you can see it in the following way. It's either A annihilates the vacuum or A dagger annihilates the vacuum, but they're different vacuums. And the one that Alex has been talking about is how does he make sense of a theory where it's what we call the creation operator that annihilates the vacuum. That's why you get the negative energy. What Carl and I looked at was the normal case where A annihilates the vacuum.
No.
And in that
case, normal A annihilates the vacuum.
Yeah, the normal A, yes, annihilates the vacuum. And in that case, we asked, can we construct an inner product that is positive definite? And the answer is, you don't take the ket and contract it with its Hermitian conjugate. That's the one that's negative, and that's the headache. You contract it with its PT conjugate.
Yeah.
And that's the case that we studied. And then we discovered that we could construct a consistent quantum theory. I then we did it initially for the Phys.Rev.Lett case, which is just a quantum mechanical. But then later on, we went on and we did the quantum field theory. And everything carries over. The question you could ask, which in a sense was what Masoud may have been asking Alex, is you have your theory, you've got your classical theory, write down the path integral. Does the path integral exist? And that would tell you that you also got a good quantum mechanics. The work that Carl and I did was the case that we solved with the PT. Then we found that the path integral did exist. Mm-hmm. And that's the key. That was the key point, which makes the quantum theory sensible. Okay. And the other thing that you asked, and Alex has been doing this, is we did make a continuation into the complex plane, and exactly as Alex did. Only what we found was we needed to go into the complex plane in order to get the path integral to exist.
Because you need to normalize the wave function appropriately.
Yeah.
Recall.
You see,
essentially, it's saying, can we get the wave functions to be bounded at infinity?
Yeah, exactly. Yeah,
let me
paper, actually.
Maybe explain a bit more of what we are doing and what is the difference between us and PT symmetric case. So for us, this imaginary trick is only a trick to motivate the system. After that, we don't care. Formally speaking, we could derive it from first principle, just assuming this minus and perform the same steps as what Darboux and Liouville have done. So we don't need it. You see, the point is we don't, in our neither proof nor in anywhere else, we use this transformation to complex values. It's only to basically get the first system, and after that, we don't care. Formally speaking, I could give it to you, and you would not know from where it came from. So the point is that for us, this quantity J, LV. This is our, so to say, energy, right? So think of the only way. If you want to find now quantum mechanics, let's say you want to consider stationary states. What you would need to do, you need to solve a system of two static or stationary Schrödinger equations with this guy applied on state vector and with the Hamiltonian applied on state vector. And now suppose in reality what you can do, forget about the Hamiltonian, start from this guy. And from this guy, you know that it's perfectly well-defined system with the minimum of your potential. You expand around the minimum, you know what is your A and A tagger. They will be standard for an oscillator, right? After that, you write everything if you want perturbatively, and you can construct whole Hilbert space in an absolutely normal way. The only thing, it's how to solve second Schrödinger equation in that case.
I see. Okay.
But formally speaking, you could immediately see that the spectrum of eigenvalues for this operator is discrete, as it should be for Hamiltonian positive energy and the potential, which is a potential well, bounded from below, unbounded from above.
Okay.
Without
this
any
is
valence.
slightly,
That's important.
so this is different than saying you can choose the vacuum just based on which operator annihilates it, correct? I mean, I'm understanding this is a different thing.
Yeah. It's a different thing because you see what we claim here, it's a highly non-trivial statement. You take this integral of motion, you find minimum of potential, so to say, potential energy U. You expand around it, and you know this is your stable, classically stable configuration. Quantum mechanically, expand around this, and then you will see everything. For example, look here. You can expand around here or around here. Perturbatively, it will be fine. Up to energies going up to here, because solutions cannot escape, right? So you just stay here, and you will rotate in like whatever, like inside of this potential well. Of course, if you go higher, that's non-perturbative statement anymore. That will be harder to analyze.
Yeah.
But otherwise, it's okay. So basically, for us, it's a major problem is in this quantum mechanical treatment is to maybe try to use some clever trick from something, I don't know from what, maybe Irina could tell me, from some, abusing the symmetry in this problem. And maybe to say something more exact. Because clearly we can do quasi-classics when we're above everything. Basically, I don't know whether you see my pointer. If we're here, just strange potential shape, but then it's all quasi-classical. Or we can go here and use perturbation theory. Or we can solve it numerically. That's also okay. But I mean, it's crystal clear that the whole thing is just well-defined.
Yeah.
With normal norm, I will introduce normal A killing my vacuum state, so it will be all standard.
It's not that you traded the negative norm for negative energy.
Yeah.
I see. Yeah,
And you see, we don't need to, after that, if I formulate use this system, I don't need any negative, basically any imaginary continuation and so on. And that's, by the way, poses a very important question raised also by Philip, what to do with path integral? Because in path integral, we know that path integral is only well-defined in actually Euclidean. And here, to do Euclidean is not easy because I have a wrong relative sign between them.
Well,
that would be a very interesting situation. I don't know how to.
It turns out that for the Pi-Suhlenbeck oscillator, it doesn't work that way. If you have a real coordinates that you start with, you are correct. The path integral exists in Euclidean space. That's Hawking and Hertog. It does not exist in Lorentzian space. Now, what that means is that the Wick rotation fails.
Yep.
Because and so what you learn from the Euclidean is not helpful. Now, if you do the continuation that Carl and I do, then you find that now the Lorentzian path integral exists and the Euclidean one does not. And yet again, the Wick rotation fails. So that's why I'm not a big fan of Euclidean field theory, simply because you have to show that if you're going to be learning something about the Minkowski theory, you've got to be able to show that the Wick rotation doesn't give you a contribution from the circle at infinity. And what I found was with the Pi-Suhlenbeck is that this is a closed form model where you do get a contribution from the circle. And in fact, if you go back to Hawking and Hertog's paper, they actually said the Euclidean path integral exists, but the Lorentzian doesn't. You see, they actually they made that point in their paper. So there was a problem. So there was a problem with the Wick rotation. If I, without hogging the talk, if I can just respond to Jeff one more comment. You asked what is PT useful for? If you have an antilinear symmetry like PT, for every energy E, there's a complex conjugate. And so there exist systems where the energies come in complex conjugate pairs, and they have been explored experimentally, and they're now well established. They go under the name of gain and loss. And however, if you have a theory that you don't know what its spectrum is, and you discover one that with the E and the E star, if all of the energies are real and the space of states is complete, then you can transform to a Hermitian operator. And basically that was the paper that Carl and I published in Phys.Rev.Lett. We discovered that there was a canonical transformation that got us to a manifestly Hermitian form. So in that case, once you have all eigenvalues real, eigenspectrum complete, you know that there's a hidden Hermitian symmetry. But until you've shown that all the energies are real and the eigenfunctions are complete, you don't know that. Now, why this is so important is because two things. One is, in the complex conjugate energy case, the energies are not real, but the wave functions are still complete. But when you make the transition from all energies real to complex pairs, at the transition point, the theory becomes Jordan block. And then the energies are incomplete. And that's a case which you simply don't get in Hermitian quantum mechanics. And I'm interested in that because it turns out that that's how conformal gravity happens to work. It happens to be a Jordan block theory. Makes it very unusual.
Yeah, I'm also very interested. Thank you.
Yeah, you're welcome.
Okay. Thank you, Philip, for your comments. And more questions, please?
I should have maybe a fast question, Alex.
Okay, please.
Very good.
So in your analysis, you always consider the second order formulation where you have two derivatives with a minus sign in one of the degree of freedom. And I think in the first example, you showed that you can recast this second order formulation in terms of a higher derivative one. You mentioned one slide. But can you always do that in all the examples that you considered?
I think in this example, you can also do it. It just becomes, it's usually not that pleasant, unfortunately. It does not give you a nice, simple Lagrangian, written in true, normal, explicit terms. That's a problem. But yeah, one can do it. Okay. One can write it as basically a system with a secondary, dependent on second derivatives.
Yeah, because I was wondering whether you can always map this type of ghost into an Ostrogasti ghost, but you are saying that is possible.
I think, yeah. I think it is. I think it is possible. Probably there are some limitations, like some small one, but as far as I remember, for this case, it was possible.
If I may just comment, if you have a propagator which goes like 1 over k squared minus m1 squared plus 1 over k squared minus m2 squared, it doesn't map to a fourth order theory. At least I don't think it does. It's only when you have the relative minus sign that you could recover that same propagator by a fourth order differential equation.
No, just for the free theory, I was wondering whether if you put some potential, you can always do that, because Alex was considering very specific type of potentials.
Well, I'd be surprised if you could always do it, but that's up to Alex.
Okay, no, I think you can actually do it.
Okay.
There were some limitations, but I don't think they were applicable for these cases. I think in most situations, this might, you see, it may be not immediately clear because, like, you see, like in this example, which I showed at the beginning, formally what you get from Ostrogradsky is this, right? I don't know whether you guys can see it.
Yeah.
And only after you introduce canonical transformation, you get this. Of course, this is a linear system. In reality, it should not matter, right?
Mm-hmm.
You could even decouple them.
Yeah, it is just free theory.
Right. But you know, this structure, I think, of going from Ostrogradsky to px squared minus py squared, this can always be done through this construction.
Yeah.
Because in reality, many of the things remain kind of the same. So now, formally speaking, you can invert this relation, this px, py, write some potential, and immediately go back in a sense.
Mm-hmm.
It's just not. I mean, it's a bit ugly, but otherwise okay.
And just one last question. You mentioned that you were doing also simulation for continuum cases, like with fields.
Yeah.
In that case, what type of potential were you considering?
Look, actually, if you're considering potential, you see, we have done a very simple kind of adjustment. Actually, we were doing something super naive, you know, very naive. Take this is scalar field theory, right? So now this is, let's say, demu psi. Okay, for Lagrangian, it would be demu phi squared minus, let's say, m squared phi squared. Then here, okay, it's better probably to keep the same mass. In that case, even though it's not that important. Then you take the same thing with minus for psi, and then here you would write phi and psi.
Ah, this type of non-polynomial potential.
Yeah, then very easy, right? So basically, it's a normal kind of field theory, and that's it.
I see.
But I mean, we also were doing it for as far as I remember, for some of the polynomial cases. But it's you see, it's in this very naive version of writing it covariantly. So basically, your zero mode does correspond to this scalar to this mechanical system. And of course, if you departure from zero mode, it's not the case anymore.
Mm-hmm. Okay, thanks.
Okay, more questions, please. I don't see more questions. Let's thank Alexander once again. It is very instructive talk, so we can speak about ghost, non-ghost without taking into account interaction. This is a short comments. I like very much this talk. So thank you very much.
Thanks a lot. Thanks a lot.
Alex.
Nice to
Alex,
see you all, guys.
Don't forget to send us your presentation.
Sure. Do you need PDF or Keynote?
Yeah, maybe PDF is better.
PDF is better. It's better.
Okay,
yes.
but do I need to put all the binding stages or just make a one file? Because
one PDF file. One PDF file.
And
okay.
if you have some the same file just to show different formula, usually it make more bigger PDF. Don't do like this because it will be too big presentation, please.
Yeah. Otherwise, it's like hundreds pages.
Indeed, yeah.
Okay, it will be 1,000 pages. Okay, thank you very much.
Great. Thanks a lot. Thanks a lot.
Thank you.
It was great to see you all.
See you next time, Alex.
If you have any questions, write.
Mm-hmm.
I will try to reply.
Alexei Koshelев, are you here? Alexei?
He's probably
he was
in
busy.
Shanghai.
He's Shanghai. Are you? You're in Belgium? Yes.
He's in Belgium, yeah.
Belgium. Maybe we can speak with you Saturday. What do you think? Can you hear me?
I think he was busy.
Okay. I will write. Okay, thank you very much. Yes.
Okay, thanks a lot.
Bye.
Thanks again, Alex.
See you.
Bye-bye.
Looking forward to see you somewhere. Ciao.